Well, hello, everybody. I'm delighted to be here. Thank you, Tim, for the opportunity to share work with you. A little bit about myself. I'm an electronic engineer. I've been working on the radar industry for the last 20 years. Different type of radars, and specifically with weather radar for the last 12 years. I don't work for our National Weather Service, but I work with them. I work for a manufacturing company, which is INVAP. And today I'm going to talk about the overall process we've been following for the last 5-7 years to go from radar composite, like the one in the left, to a radar composite, like the one in the right. The screen is...
It's not shared.
Not sure, okay.
Okay, thank you. Very sorry about that.
Okay, not so brief introduction, but since this is from Argentina and this is an European workshop, so we will be talking about the SINARAME network. The SINARAME network is an ongoing long-term government project to fill all of Argentina with weather radars. When it started in September of 2011, there were only 3 C-band weather radars operational. Now we have 15. The 12 new radars have been built by INVAP, the company I work for. This is the radar. It's been completely designed, developed in Argentina. Of course, we did not manufacture every single piece. We have providers for some of the parts. The project, SINARAME project, is still under execution. We are right now on the stage 3. We expect to have 21 radars by the end of next year. So since the beginning, since the first operational radar from SINARAME, which we call RFI, since the first RFI radar was put into operation in Córdoba, this one, we got what you all know. We got a lot of contamination from radio frequency interferences. In Argentina, in particular, it's mainly because of Wi-Fi routers and links, traffic cameras, and that kind of infrastructure. We have explored different methods to try to mitigate this. The best effective is locating the offending sources and shutting them down, or switching for different technology, different bands. But in practice, that is very difficult to manage. We explored also tuning the transmitting receiving frequency of the radars in different channels. That the improvement was marginal, because new routers, new sources or interferences are always going up. And we also tried with analog filters, specifically at the input of the receiver. None of those really worked out. So we started working on a digital filter, which works on IQ time series data. They work on a pulse-to-pulse basis. We statistically identified contaminated cells, pixels, in the pictures, and we remove the contaminated data before the products are calculated. So in a typical operational strategy, let's say we are transmitting 32 pulses on a contaminated cell, you will end up calculating the products for, let's say, 30 pulses, maybe 20 pulses. We have found that overall there is a visible improvement in the data quality. Flow HB goes higher. The standard deviation gets lower. So far, this has been working fine. This image here, it's recent. You can watch this radar composite online at any time. Here is the link. These are images generated by our National Weather Service. You also have a Colmax representation for the different radars. Okay, this was a long project. It took us between 5 to 7 years to complete. It involved different works from actual measurements on the sites, connecting instrument directly to the radar antenna in order to see or hear the same that the radar is receiving. When we decided to go with the software solution, phase 1 involved processing real weather data, synthetically contaminated with real radio frequency interference data. I will talk briefly about this because I already did a presentation, a poster actually, on Locarno last year for ERA. This presentation will be focused on phase 2, which is processing archives of real data. And I will speak a little bit about phase 3, which is actually running the filter on the field. Of course, we as manufacturers can do this all by our own. We did this in close collaboration with different institutes of Argentina. Our main user is our National Weather Services, Servicio Meteorológico Nacional. We also work closely with people from different universities, in particular with Universidad Nacional de Córdoba, which is the place where we place our phase radar, or the first one called RMA 1. And the sponsor for all this project and the institution that is managing this project from the side of the state is Secretaría de Infraestructura y Política Hídrica. Okay, this is phase 1. The methodology was finding, handpicking, actually, real weather data from a site that we have in Argentina, which is under the coverture area of the radar. There is very low population, so there were naturally no many sources of interferences. We waited for the right atmospheric conditions so that the antenna beam doesn't get the contamination. On the other side, the lower one, we went to our heavily contaminated sites, which are located in our biggest cities, such as Buenos Aires and Córdoba, and putting the transmitter off, we collected data, and we mathematically added up on an IQ level basis, so we get amplitude and phase information, and we processes that with our filter. So that this is the original weather data, 3 different cases. This is the contaminated set. And this one is the clean set after applying the filter. We have done this on the lab. It's all offline. And the good part of this is that we have full control over the data. We can also simulate different amplitudes for the interference sources. And we can compare our reference dataset with our filtered dataset. Here's an example for reflectivity. And what you can see, the lower right, is the mathematical difference of the clean original source and the filtered. This one on the upper right is the contaminated set. And by studying the difference, which we would like to be 0 when there is a storm, and we would like to be a maximum when there is only interference, we were able to characterize the filter performance. We have a few parameters for the filter in order to increase its filtering aggressiveness. But if you go for full aggressive filter, you end up having false positive. This is the detection theory for radars. If you want to detect and remove all interferences, you end up having false alarm. That is, the filter detects signal, weather signal, as if were interferences, and ended up deteriorating the signal. I believe here you can appreciate with more detail the real impact that radio frequency interferences has in data quality. We could not be able to recuperate that, which is quite visible from the difference. Okay, moving on to phase 2. Again, we selected real data. This time is data, IQ data from our archives. Luckily for us, we have access to all the radars in our network, and we have the possibility of saving data to disk. We only can do that for few scans because the amount of data is really huge. We are talking about terabytes of data here. And in this particular data, we don't have control, the level of contamination or the power. But this is so close as you can be to real performance on real scenario. So the methodology here is to use the unfiltered data as a reference, filter it, and calculate the difference so that you can see how much the filter has filtered and whether it has filtered the signal that you want to remain untouched. We selected 3 scenarios. The first one is clear air, second one with rain, and in this case, I don't know if you can see it from them, but there is a smoke plume here from a big fire. So I will go back and forward so that you can see a sort of animation. This is the effect of applying the filter on and filter off. And this is the difference, so that you can see that the weather signal remains mostly unaffected, but the contamination is mostly removed or at least attenuated. We have repeated this procedure for all the radar products. I will only show 2 here. Reflectivity and ρHV, the correlation coefficient. Again, the same data set, unfiltered, and with the filter on. Here, you can see the Sierras of Córdoba, that is ground clutter. And this one here is also ground clutter from anomalous propagation. For these images, only the radio frequency interference filter was turning on, not ground clutter, not anything else. So unfiltered, filtered difference. Here you can see the maximum value of the difference. But let's move on and see a few more focused examples. This is the PPI from the rain case. And we have cut on slides. We will focus on this. This is the same, but in a range versus time, or range versus azimuth in this case, because it's a PP representation. The circles in white shows where the filter is working as we are intended it. So removing the contamination, but letting the interesting signal, the weather signal, untouched, while the red one and the blue one shows where the filter is not performing optimal in the sense that it's filtering a little bit of weather. Again, I will move back and forwards so that you can see. And here in this label, you can see the set of the probability of false alarm. The lower the number, the best the filter will perform to keep weather, and the worse the detection. So this is a relaxed configuration, very low probability of false alarm. This one is moderate, and this one is an aggressive one. It's difficult to see the differences while the slides are still. So again, I will move back and forward so you can see an animation. Take a look here, for example. Can you see the cell as it appears and disappears? I'm not sure if the resolution is good enough. Which is evident is that the contaminated radial goes away. And it's very subtle, but as we lower the probability of false alarm, this unwanted signal here disappears. Can you see it? But also we lose the edge of the storm. And here we can see the same example, but in flow HB. Again, same parameter set. In this case, you will be able to see how data quality improves. The correlation coefficient goes higher when there is weather and goes lower when there is only noise. But again, in the case of weather, at the edge, you lose a little bit. This is another example. This is with the smoke plume. Again, the circles in white are focused where the filter is working optimal. And these are two examples where this is actually the edge of clutter, but again, where the filter is taking out signal that it shouldn't. I'm not sure if you can see that. And these are the differences. So right now, the filter has been activated in all the operational sites, only in the new radars, the RMF radars. There are 12 of those radars. The project is expanding the network. We expect to have 21 radars by the end of next year. We will be activating the filter by the means of a processor upgrade in all the sites. The actual plan that has been accorded consensus with all the institution is that we activate it on a side-by-side basis, and we follow that by a monitoring period. It goes from 1 month to 3 months, typically. It depends mainly on weather. You need to have weather in order to assess how well or how bad it is performing. Right now, of the 3 configuration I showcases, we're using the middle one, the moderate. We think that for some operational uses, aggressive would be better, but for some research, probably a less aggressive approach would be better. Unfortunately, this works inside of the radar at the IQ level data. Once you filter signal, you cannot recover it. It is gone. It's information that you lose. So I think we have found a good trade-off, and I firmly believe that this procedure, the 3 phases procedure to validate the network and working close with our users, with our customers, it's a good approach, a good model, and we're quite happy with the results. Well, acknowledgement, again, this could not be possible without all the support of our government, with all the institutions that are working with us in the continuous product improvement, in the benefit of all of our users, of all the people in Argentina, benefited for the forecasting and the alerts given by our National Weather Service. Thank you.
When I see your radar network, and you obviously have a number of radars where you have overlap between neighboring radars, have you also considered using that to verify your filter performance, using the observation from another radar that obviously has not the same interference as a verification tool as well?
Thank you for your question. We haven't done that. The reason is because our radars are quite far apart one from another. I think I have a picture of the network close to the beginning of the presentation. Here, for example, those circles are 280 kilometers. So there is no very good superposition of the coverage area. Sorry? 200, 250, 280.
Sorry, all the PPI showed were
Yes, everything.
lowest elevation.
Yes, the PPI from the data processed in lab offline, yes, it's the lower elevation scan, 0.5. Those were all examples from Cordoba radar. While the black images, like this one, those are Colmax, not PPI. Mike.
Thank you, EWD. Just from understanding, so your approach assumes that there is one pulse not having not an interference with an RFI, or is that one requirement, right? So if if all the pulses are have an interference signal, this approach doesn't work, right?
Yes, if you, it's quite unlikely, but it happens from time to time.
Okay.
That from one cell in range, from one cells, you lose enough pulses so that the product cannot be calculated. For example, in the case of Doppler, if you are using not the frequency domain processing, but the pulse pair processing. If you have the bad luck, you lose one pulse every. You end up having half of the pulses, but you cannot process the Doppler. So you end up having a hole in the data. We are not using interpolation. It's only calculation over clean data.
The filter that you tune, it's parameterization radar independent.
The parameterization is dependent on the scanning strategy. It depends. Well, this talk is not about the algorithm, but the method implies statistics to try to detect what appears to be an interference, a pulsed interference. This doesn't work for other sources of interference, like the sun, for example, which is not pulsed. So we apply the statistics to decide whether cell is contaminated or not. In order to maximize the detection probability, you have to keep in mind the length of the pulse, because that is related to the amount of energy that is transmitted, and also the PRF. So our filters are tuned to each and every one of the operational scanning that we are using in Argentina. Right now, we have 3 different types of configurations.
Okay, thank you very much.